Picture the setup first, because nothing here is abstract yet. You have a source that sends particles forward. In front of it is a barrier with two very narrow slits close together. Farther back is a screen that records where each particle lands. That's the entire experiment. Now start with classical expectations. If you shoot tiny particles, like marbles, each one must go through either the left slit or the right slit. On the screen, you'd expect two fuzzy bands, one behind each slit. That's it. If instead you send waves, like water waves or classical light waves, each slit acts like a source. The waves spread out, overlap, and interfere. Where crests meet crests, the wave is strong. Where crests meet troughs, they cancel. On the screen, you get a pattern of bright and dark stripes called an interference pattern. So far, nothing strange. Now do the real experiment with quantum particles, like photons or electrons. The screen doesn't light up smoothly. Each particle arrives as a single, localized dot. One particle, one hit. That looks exactly like particles. But if you let many of these hits build up over time, the dots don't form two blobs. They form an interference pattern, bright and dark fringes, just like waves. Even more unsettling, this still happens if you send the particles one at a time, so slowly that only one particle is ever in the apparatus. Each event looks particle-like. The overall pattern is wave-like. This is where classical reasoning fails. Quantum mechanics explains this with a new rule. You don't assign ordinary probabilities to went through slit 1 or went through slit 2. Instead, you assign probability amplitudes. Call them psi1 and psi2. If there is no way, even in principle, to know which slit the particle took, the rule is simple but strange. You add the amplitudes first, then square the result. So the probability on the screen is the square of psi1 plus psi2. When you expand that square, you get two normal probability terms and an extra cross term. That extra term can be positive in some places and negative in others. That's interference. Bright fringes come from reinforcement. Dark fringes come from cancellation. Now ask the obvious question. Which slit did the particle actually go through? Here's the careful answer. If the experiment is set up so that no which path information exists anywhere in the universe, then that question does not have a definite answer. The theory doesn't say the particle secretly chose a slit and hid it from us. It says the alternatives are part of a single quantum state. Change the setup, though, and everything changes. Put a detector at the slits that can record which one the particle passes through. The interference pattern disappears. The screen now shows two single-slit patterns added together, exactly what you'd expect for particles. This is not because a human looked. It's because the particle became physically correlated with the detector and the environment. That correlation destroys the phase relationship between the two paths. This process is called decoherence. When path information exists, amplitudes no longer combine to interfere. There's a precise trade-off here. The more accurately you can know the path, the less visible the interference becomes. You never get both perfectly at once. This experiment isn't just about light. Electrons do it, atoms do it, even large molecules do it, as long as they're isolated well enough from their environment. The only reason everyday objects don't show this behavior is that they decohere almost instantly. So what does the double-slit experiment really tell us? It tells us that nature does not follow classical either-or logic at a fundamental level. When alternatives are indistinguishable, quantum mechanics demands that we add amplitudes, not probabilities. From that single rule come interference, wave-particle duality, and the need for quantum mechanics itself. That's why this experiment is famous. It's the smallest, cleanest place where the classical picture breaks and the quantum one has to take over.